Hello, and welcome to the Nocturnal Astronomer. I'm your host, Atlas Reed, and tonight we're going to explore one of the most fundamental stories in the cosmos, the life cycle of a star. From the cold darkness of stellar nurseries to the spectacular finale of supernova explosions, we'll journey through billions of years of stellar evolution. We'll discover how gravity shapes clouds of gas into burning spheres of plasma, how stars maintain their brilliance for millions or billions of years, and what determines whether a star will fade gently or explode in one of the universe's most energetic events. If you enjoy these types of videos, please give this one a thumbs up and consider subscribing to the channel. I'd also love to know where you're watching from and what time it is for you right now. Drop a comment below and let me know if you're watching under the stars or tucked into bed somewhere on our little blue planet. Let's dive in. Stars are born in vast clouds of gas and dust called molecular clouds, sometimes known as stellar nurseries. These clouds can stretch across hundreds of light years and contain enough material to create thousands of stars. The primary ingredient is hydrogen, the simplest and most abundant element in the universe, along with helium and trace amounts of heavier elements. The temperature in these clouds hovers just a few degrees above absolute zero, making them some of the coldest places in the galaxy. The process of star formation begins when something disturbs the delicate balance within a molecular cloud. This disturbance might come from the shock wave of a nearby supernova, the collision of two clouds, or the gravitational influence of a passing spiral arm in the galaxy. Whatever the cause, regions within the cloud begin to collapse under their own gravity. Think of it like a snowball rolling down a hill, gathering more snow as it goes. As the cloud collapses, it pulls in more material, and the gravitational pull becomes stronger. As the collapsing region contracts, it begins to spin faster, much like a figure skater pulling in their arms during a pirouette. This rotation causes the material to flatten into a disk with a dense center. The center becomes increasingly hot and dense as gravitational energy converts into heat. This process can take around 100,000 years for a star similar to our Sun, which may seem long to us but is remarkably quick on cosmic timescales. Within the rotating disk, the temperature and pressure at the core continue to rise. When the core temperature reaches around 10 million degrees Kelvin, something extraordinary happens. Hydrogen nuclei, which normally repel each other due to their positive charges, are forced close enough together that the strong nuclear force takes over, fusing them into helium. This process, called nuclear fusion, releases tremendous amounts of energy. The moment fusion begins marks the birth of a true star, and this newborn star is called a main sequence star. The energy released by fusion creates an outward pressure that balances the inward pull of gravity. This balance is crucial. Without it, the star would either collapse under its own weight or blow itself apart. The leftover material in the disk may eventually form planets, moons, asteroids, and comets, creating a solar system around the young star. Our own Sun formed this way approximately 4.6 billion years ago, along with the Earth and all the other bodies in our solar system. The main sequence is the longest and most stable phase in a star's existence. During this time, the star steadily fuses hydrogen into helium in its core, releasing energy that we perceive as light and heat. For a star like our Sun, this phase lasts roughly 10 billion years. More massive stars burn through their fuel much faster and may spend only a few million years on the main sequence, while smaller stars can remain stable for trillions of years, longer than the current age of the universe. The mass of a star determines almost everything about its existence. Massive stars, those with more than 8 times the mass of the Sun, burn incredibly hot and bright. their cores reach higher temperatures, which accelerates the fusion process. These stars appear blue or white and emit enormous amounts of ultraviolet radiation. In contrast, stars with less mass than the Sun burn cooler and dimmer, appearing red or orange. These red dwarf stars are the most common type in the galaxy, though they're often too dim to see with the naked eye from Earth. The balance between gravity and fusion pressure remains constant throughout the main sequence phase. Picture a tug of war where both sides are perfectly matched. Gravity constantly tries to squeeze the star inward, while the pressure from fusion pushes outward with equal force. This equilibrium keeps the star at a stable size and temperature for most of its existence. The Sun, for example, has maintained roughly the same diameter for billions of years and will continue to do so for billions more. Stars on the main sequence exhibit a clear relationship between their mass, temperature, and brightness. This relationship, first documented by astronomers Ejner Hertzsprung and Henry Norris Russell in the early 20th century, allows us to understand stellar properties just by observing their color and brightness. The resulting diagram, called the Hertzsprung-Russell diagram, remains one of the most important tools in astronomy. It shows that most stars fall along a diagonal line from hot, bright stars in the upper left to cool, dim stars in the lower right. During the main sequence phase, a star like the Sun converts approximately 600 million tons of hydrogen into helium every second. Despite this enormous rate of consumption, the Sun has enough hydrogen to continue this process for another 5 billion years. The helium produced by fusion accumulates in the core, gradually building up like ash in a fireplace. Eventually, this buildup will bring about significant changes, but for now, the star remains peaceful and stable, steadily shining into the cosmos. When a star exhausts the hydrogen in its core, the balance that defined the main sequence comes to an end. With no fusion occurring in the center, there is nothing to counteract gravity's inward pull. The core begins to contract, and as it does, it heats up due to gravitational squeezing. This might seem counterintuitive, but when you squeeze a gas, it gets hotter, just as a bicycle pump warms up when you push air inside it. The contracting core becomes hot enough to ignite hydrogen fusion in a shell surrounding the inert helium center. This shell burning produces even more energy than the core fusion did during the main sequence. The additional energy causes the outer layers of the star to expand dramatically. The star grows to hundreds of times its original size, transforming into what astronomers call a red giant. Despite its larger size, the surface cools because the energy is spread over a much greater area, giving the star a reddish appearance. For a star like our Sun, the red giant phase will begin in approximately 5 billion years. The Sun will swell to a size that may engulf Mercury and Venus, and possibly reach Earth's orbit. Even if Earth survives being swallowed, the intense heat will make our planet uninhabitable, boiling away the oceans and stripping away the atmosphere. This might sound catastrophic, but it's a natural part of stellar evolution that happens to every star in this mass range. As the helium core continues to contract and heat up, it eventually reaches a temperature of about 100 million degrees Kelvin. At this point, helium nuclei can overcome their mutual repulsion and fuse together, forming carbon and oxygen. This process is called helium fusion, or the triple alpha process, because it requires 3 helium nuclei, also known as alpha particles, to combine. For stars with less than about 2 solar masses, helium fusion begins explosively in an event called the helium flash, briefly generating as much energy as an entire galaxy before settling into stable helium burning. The star now has 2 fusion zones, a helium burning core surrounded by a hydrogen burning shell. This structure will persist for a time, though not nearly as long as the main sequence phase. Helium fusion proceeds much more quickly than hydrogen fusion, so this phase might last only a few 100 million years for a star like the Sun. The star's appearance during this time can vary, but it generally remains large and luminous, continuing its time as a red giant while it steadily converts helium into carbon and oxygen in its core. When a star of low to medium mass, up to about 8 times the mass of the Sun, exhausts the helium in its core, it faces a similar situation to before. The core, now made of carbon and oxygen, begins to contract again. However, for these stars, the core never becomes hot enough to fuse carbon. The temperature required for carbon fusion is around 600 million degrees Kelvin, and only more massive stars can achieve this. Without fusion to support it, the core contracts until the electrons within it are packed so tightly that quantum mechanical effects come into play. Electrons resist being squeezed beyond a certain point due to a principle called electron degeneracy pressure. This isn't a temperature-related pressure, but rather a consequence of the Pauli exclusion principle, which states that no 2 electrons can occupy the same quantum state. Think of it like trying to pack too many books on a shelf. Eventually, they simply won't fit, no matter how hard you push. Meanwhile, the outer layers of the star become increasingly unstable. Thermal pulses caused by intermittent shell burning push material outward in waves. The star's powerful stellar current, a stream of charged particles flowing away from its surface, grows stronger. Eventually, the outer envelope of the star drifts away into space, forming an expanding shell of glowing gas called a planetary nebula. Despite the name, these have nothing to do with planets. Early astronomers thought they resembled planets through their telescopes, and the name stuck. Planetary nebulae are among the most beautiful structures in the universe. They come in various shapes: spherical shells, bipolar lobes, intricate spirals, and multilayered structures. These shapes arise from factors such as the star's rotation, magnetic fields, and whether it has a binary companion. The gas in the nebula glows because ultraviolet light from the hot central star excites the atoms, causing them to emit light at specific wavelengths. These nebulae enrich the interstellar medium with elements created in the star, including carbon, nitrogen, and oxygen, which will eventually become part of new stars, planets, and perhaps even biological forms. At the center of the planetary nebula sits the exposed core of the former star, now called a white dwarf. This body is incredibly dense. A white dwarf with the mass of the Sun would be about the size of Earth. A teaspoon of white dwarf material would weigh several tons on Earth. The white dwarf is initially very hot, with surface temperatures exceeding 100,000 degrees Kelvin, but it has no internal energy source. It will gradually cool over billions of years, fading from white to yellow to red and eventually becoming a black dwarf, though the universe is not yet old enough for any black dwarfs to exist. Stars with initial masses greater than about 8 times the mass of the Sun follow a different and more dramatic evolutionary path. These massive stars burn through their hydrogen fuel much more quickly than their smaller counterparts, spending perhaps only 10 to 20 million years on the main sequence. Their high core temperatures allow them to fuse elements beyond helium, climbing up the periodic table in a series of burning stages. After exhausting hydrogen, a massive star expands into a supergiant, even larger than a red giant. The star's core contracts and heats up, igniting helium fusion. Once helium is depleted, the core contracts again, reaching the temperatures needed for carbon fusion. This pattern continues through several stages. Carbon fuses into neon and magnesium, neon fuses into oxygen and magnesium, oxygen fuses into silicon and sulfur, and finally, silicon fuses into iron. Each stage burns at progressively higher temperatures and proceeds more rapidly than the last. The silicon burning phase lasts only about 1 day before producing an iron core. This is a critical moment in the star's existence. Iron is the most stable nucleus, meaning that fusing iron requires energy input rather than releasing energy. Iron is effectively nuclear ash. When the iron core grows to about 1.4 solar masses, the Chandrasekhar limit, it can no longer support itself against gravity, even with electron degeneracy pressure. At this point, the core collapses catastrophically. In less than a second, the core implodes from roughly the size of Earth to a sphere only 20 kilometers across. The electrons are forced to combine with protons, forming neutrons and releasing neutrinos. The collapse halts when the neutrons themselves become degenerate, creating a neutron star. The infalling material rebounds off this rigid neutron core, generating a powerful shock wave that races outward through the star. This shock wave, aided by the intense neutrino flux, blows the star apart in a supernova explosion. The explosion releases more energy in a few seconds than the star emitted during its entire main sequence phase. For a brief period, the supernova can outshine an entire galaxy of hundreds of billions of stars. The explosion also creates conditions extreme enough to forge elements heavier than iron, including gold, platinum, and uranium. Every atom of gold in your jewelry, every atom of uranium in Earth's core, was created in a supernova explosion billions of years ago. The remnant left behind after a supernova depends on the mass of the collapsing core. If the core's mass is between about 1.4 and 3 solar masses, it forms a neutron star. These are among the strangest and most extreme bodies in the universe. A neutron star packs more mass than the Sun into a sphere only about 20 kilometers in diameter, roughly the size of a city. The density is so extreme that a sugar cube of neutron star material would weigh about 1 billion tons on Earth. Neutron stars are composed almost entirely of neutrons packed together as tightly as the nuclei of atoms. The pressure and density in the core may be high enough to create exotic states of matter that cannot exist anywhere else in the universe. The surface gravity of a neutron star is approximately 200 billion times stronger than Earth's. If you could somehow stand on a neutron star, you would be flattened to a layer less than an atom thick. The magnetic fields of neutron stars are the strongest known in the universe, trillions of times more powerful than any magnetic field we can create on Earth. Some neutron stars become pulsars, sending out beams of radiation from their magnetic poles as they spin. If these beams sweep across Earth, we detect regular pulses of radio waves, X-rays, or gamma rays. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, who initially wondered if the regular signals might be from an alien civilization. Pulsars can spin incredibly fast, with some rotating hundreds of times per second. They serve as precise cosmic clocks, and astronomers use them to study everything from gravitational waves to the nature of matter under extreme conditions. If the collapsing core has a mass greater than about 3 solar masses, not even neutron degeneracy pressure can halt the collapse. Nothing can stop gravity's pull, and the core continues to collapse into a single point of infinite density called a singularity, surrounded by an event horizon. This is a black hole. The event horizon marks the point of no return. Once something crosses this boundary, not even light can escape. This is why these bodies appear completely black. Black holes come in different sizes. Stellar mass black holes, formed from supernova remnants, typically have masses between 5 and several dozen times the mass of the Sun's supermassive black holes. Found at the centers of most galaxies, including our own Milky Way, can have masses of millions or billions of solar masses. Despite their fearsome reputation, black holes obey the same laws of physics as everything else. They have gravity, but they don't roam around sucking up everything nearby. If the sun were suddenly replaced by a black hole of the same mass, Earth would continue orbiting exactly as it does now, though it would certainly get very cold and dark. The death of stars, whether gentle or violent, serves a crucial purpose in the cosmos. Stars are the universe's great forges, creating nearly all the elements heavier than hydrogen and helium. The Big Bang produced only the lightest elements. Everything else, from the oxygen you breathe to the calcium in your bones to the iron in your blood, was manufactured in the cores of stars or during supernova explosions. This makes the famous Carl Sagan quote literally true: "We are made of star stuff." Astronomers classify stars into different populations based on their metal content. Population 3 stars were the very first stars in the universe, born just a few 100 million years after the Big Bang. These primordial giants contained essentially no heavy elements because none yet existed. They were likely massive, perhaps 100 to 300 times the mass of our sun, and burned extremely hot and bright. Their existence was brief, maybe only a few million years, before they exploded as supernovae, seeding the universe with the first carbon, oxygen, silicon, and iron. Population 2 stars formed from gas clouds that had been enriched by those first supernovae. These stars have low but measurable amounts of heavy elements, typically 1/10 to 100th the metal content of our sun. Many population 2 stars are found in globular clusters, dense spherical collections of hundreds of thousands of ancient stars that orbit the outskirts of galaxies. Some of these stars are among the oldest known, with ages approaching 13 billion years, nearly as old as the universe itself. Population 1 stars, including our sun, are the most recent generation. They formed from material that had been processed through multiple generations of earlier stars. The sun's composition is approximately 71% hydrogen, 27% helium, and 2% heavier elements. That 2% may seem small, but it's crucial. Without those heavy elements, rocky planets like Earth could not exist, and neither could the chemistry that enables biological systems. Every carbon atom in your DNA, every iron atom in your hemoglobin, represents the accumulated output of stellar nucleosynthesis over billions of years. The chemical evolution of the universe is an ongoing process. When a star dies, it returns much of its material to space. Planetary nebulae gently release their outer envelopes, while supernovae violently expel most of the star's mass. This enriched material, now containing dozens of different elements, mixes with the existing interstellar medium. The concentration of heavy elements in the galaxy has been steadily increasing since the first stars formed. In another 5 billion years, stars that form will have even higher metallicity than today's stars, continuing the universe's slow but inexorable transformation from simple to complex. This chemical enrichment isn't uniform across the universe. The centers of galaxies, where star formation has been most active, tend to have higher metallicity than the outer regions. Elliptical galaxies, which experienced rapid star formation early in their history, often have higher average metallicity than spiral galaxies like the Milky Way. Studying stellar populations helps astronomers understand the history of galaxies, piece together how different regions evolved over time, and predict what the universe will look like billions of years from now. Each star is a time capsule, its chemical composition revealing the conditions when and where it formed. So far, we've discussed stars as if they exist in isolation, but the reality is far more complex and interesting. Approximately half of all stars in the galaxy are part of binary or multiple star systems, where 2 or more stars orbit their common center of mass. These stellar partnerships significantly affect how stars evolve, sometimes leading to outcomes impossible for solitary stars. The interactions between binary companions create some of the most spectacular and energetic phenomena in the universe. In a wide binary system, the two stars might be separated by hundreds or thousands of astronomical units. They orbit each other slowly over centuries or millennia, and their evolution proceeds much as it would if they were alone. However, in close binary systems, the stars can dramatically influence each other's development. If one star expands into a red giant while its companion remains on the main sequence, the giant's outer layers may reach the point where the companion's gravity pulls material away. This mass transfer can rejuvenate the receiving star, giving it fresh fuel and extending its time on the main sequence. Type Ia supernovae, some of the most important cosmological tools astronomers have, arise from binary systems containing white dwarfs. When a white dwarf accretes material from a companion star, either a red giant or another white dwarf, its mass gradually increases. If the white dwarf reaches the Chandrasekhar limit of about 1.4 solar masses, carbon fusion ignites explosively throughout the entire star. Unlike core collapse supernovae, which vary in brightness, Type Ia supernovae have remarkably consistent peak luminosities. This makes them excellent standard candles for measuring cosmic distances. Their use led to the discovery that the universe's expansion is accelerating, a finding that earned the Nobel Prize in Physics in 2011. Cataclysmic variables are another fascinating class of binary systems. These consist of a white dwarf accreting material from a close companion, typically a red dwarf or subgiant star. The material forms an accretion disk around the white dwarf, spiraling inward while heating to extremely high temperatures. Friction in the disk can cause it to periodically become unstable, leading to sudden outbursts where the system brightens by several magnitudes in a matter of hours or days. These outbursts, called dwarf novae, can repeat on timescales of weeks to years, providing astronomers with laboratories to study accretion physics and binary evolution. Even more extreme are X-ray binaries, where a neutron star or black hole accretes material from a normal star companion. The infalling material releases tremendous gravitational energy as it spirals toward the compact partner, heating to millions of degrees and emitting powerful X-rays. Some X-ray binaries show periodic outbursts where the X-ray emission suddenly increases by factors of thousands or millions. Others produce relativistic jets, streams of particles moving at nearly the speed of light, shooting away from the system's poles. These systems let us observe matter under the most extreme conditions of gravity, density, and magnetic field strength found anywhere in the universe. Binary evolution can also lead to stellar mergers. When two stars orbit closely enough, they can lose energy through gravitational wave emission, causing their orbits to gradually shrink. Eventually, they may spiral together and merge into a single body. The merger of two white dwarfs might produce a massive white dwarf, trigger a supernova, or create a neutron star. The merger of two neutron stars generates a spectacular kilonova explosion, produces gravitational waves strong enough to detect across the universe, and forges heavy elements like gold and platinum through rapid neutron capture. The first gravitational wave detection from a neutron star merger, observed in August 2017, marked the beginning of multi-messenger astronomy, where cosmic events are studied using both electromagnetic radiation and gravitational waves. The cycle continues endlessly. As we speak, new stars are forming in molecular clouds throughout our galaxy and across the universe. Many of these stars have planets, and some of those planets might harbor biological forms. In billions of years, our sun will shed its outer layers as a planetary nebula, and the carbon and oxygen in its core will eventually find their way into new stellar systems. The story of stars is not just the story of distant celestial bodies. It is our story, the story of where we came from and the cosmic processes that made our existence possible. The atoms reading these words right now were forged in stellar furnaces billions of years ago, and they will continue their cosmic journey long after our brief moment in time has passed. When you look up at the night sky, you are witnessing different chapters of stellar evolution simultaneously. That bright blue star in Orion's belt is a young, massive star that will burn brilliantly but briefly, destined to explode as a supernova in just a few million years. The reddish star Betelgeuse, also in Orion, is a red supergiant nearing the end of its existence and could go supernova anytime in the next 100,000 years. When it does, it will briefly shine as bright as the full moon, visible even during daylight. The faint red dwarfs, too dim to see without a telescope, will outlast all of them, burning steadily for trillions of years into an unimaginably distant future. Our sun sits comfortably in middle age, about halfway through its 10 billion year main sequence phase. It has been shining steadily for 4.6 billion years, providing the stable energy source that allowed biological complexity to develop on Earth. For the next 5 billion years, it will continue much as it is now, though it gradually brightens at a rate of about 10% per billion years. This slow increase means that in about 1 billion years, Earth will become too hot for most forms of existence as we know them. The oceans will begin to evaporate, and our planet's time as a habitable world will come to an end, though the sun itself will continue burning for billions of years beyond that. The timescales of stellar evolution humble us. A human existence spans perhaps 80 or 90 years. Recorded history extends back only about 5,000 years. Our species has existed for roughly 300,000 years. Yet stars measure their ages in millions or billions of years. The light from distant stars we see tonight began its journey before humans existed, before dinosaurs walked the Earth, sometimes before Earth itself formed. When we observe a galaxy 10 billion light years away, we're seeing it as it appeared when the universe was less than 4 billion years old, before our sun or solar system came into being. This vast perspective can make us feel insignificant, but it also reveals something profound. We are the universe's way of knowing itself. The atoms in your brain were forged in stellar cores and scattered by supernovae. Those atoms came together in just the right way to form structures capable of contemplating their own origin. You are, quite literally, star stuff that has become conscious, capable of understanding the nuclear physics that created the elements in your body. In all the cosmos, as far as we know, this ability to comprehend the universe is rare and precious. Stars connect us not only to the past but to the future. The elements being forged in stellar cores right now will someday be part of new worlds and perhaps new forms of awareness. The carbon atoms in your body might have been inside 5 or 6 different stars before becoming part of you. Billions of years from now, those same atoms might be part of a tree on some distant world, or a creature we cannot imagine, looking up at their own night sky and wondering about their place in the cosmos. The stellar cycle ensures that matter is endlessly recycled, transformed, and given new opportunities to organize into complex structures. Understanding stellar evolution also gives us a framework for thinking about the long-term future of the universe. Star formation cannot continue forever. As the universe ages, the available gas for making new stars gradually diminishes. In about 100 trillion years, the last star will form. After that, only the longest burning red dwarfs will remain, slowly fading over incomprehensible spans of time. Eventually, in 10 to the 40th power years, even the most stable stars will have exhausted their fuel, leaving behind white dwarfs, neutron stars, and black holes in an increasingly cold and dark universe. But that future is so distant that it's almost meaningless to contemplate. For now, for billions of years to come, the universe remains in its stellar age, a time of light and energy and possibility. And on that note, we've completed our journey through the existence cycle of stars. From the cold darkness of molecular clouds to the spectacular death throes of supernovae, we've witnessed how stars shape the universe and create the very elements that make up planets, moons, and biological forms. These processes, playing out over timescales almost impossible for us to comprehend, connect us to the cosmos in the most fundamental way imaginable. Thank you for joining me tonight on the Nocturnal Astronomer. I hope this journey through stellar evolution has given you a sense of wonder about the stars shining above you and the remarkable processes that govern their existence. Whether you're drifting off to sleep or simply pondering the night sky, remember that you're made of the same material as the stars themselves. Until next time, keep looking up.